Let's look at a result that has to do with the differentiation of the integral. This is basically an extension of part one of the fundamental theorem of calculus, where we actually differentiate an integral that's defined in the statement of the theorem. So what we want to do is extend that result. This is sometimes called Leibniz rule. So let's suppose u and v are differentiable on some common domain I, and for x in the domain I, suppose f of u of x and f of v of x are continuous. We just want to be able to integrate them. Then, if we differentiate the integral, that is, this is a function of x, that is the integral of f of t, lower limit u of x, upper limit v of x, we should get f of v of x times v prime minus f of u of x times u prime. So you're thinking that looks like the chain rule, and it basically is. So how do we prove this result? It's really not very difficult. It's like proving the result for even and odd functions. So what I'm trying to stress here is that the result on even and odd functions and this result about differentiating the integral are extremely powerful techniques. You need to know them, and they move the problem forward very quickly with very, very little effort. So for instance, when we take the x derivative of this function of x, first what we're going to do is use additivity. We'll just take 0 again. So we'll integrate f from 0 to v of x plus the integral u of x to 0. Now again, what we want to do is rig this for the fundamental theorem. This is already ready because we have the constant lower limit, variable upper limit. So to make this look similar to this or like this, what we want to do is interchange the limits of integration. So in doing that, we introduce the negative sign. So now both of these are in the form that we would like for the first part of the fundamental theorem. So now the derivative is linear, so we can apply the derivative to this function of x and the derivative to this function of x with a minus sign. So now we have the derivative of the first integral minus the derivative of the second integral. So this is ready for the fundamental theorem of calculus. But note, the upper limit is not just x, it is a function of x. So by the chain rule, we know when we take the derivative, we get f of v of x. That is, we just evaluate f at the upper limit, but then we have to multiply by the derivative of the inner function. Then minus, of course, f of u of x times the derivative of u of x. Now, you might think this is just the fundamental theorem part 2, but it's not. It's not at all related to that. The thing is here is that because we have part 1 with the differentiation of the integral, we can extend that result, and it kind of looks like what we're thinking of big F of B minus big F of A, but don't confuse it with that. It's not that at all. This is the chain rule. Now, here's a simple example. So you can make up problems to practice this result, but just make sure you've got the nice continuity. You don't want to just put up functions that don't make sense. So for instance, if we take the x derivative of this function of x, again, we've got two functions that have continuity on some common set I, and then of course the cosine function likes pretty much any real valued function, so this satisfies the hypotheses. So now what we do is we take cosine of 4x, the upper limit, times the derivative of 4x, minus, as we have here, cosine of the lower limit, cosine of x squared, times the derivative of x squared. So this will just give us a 4, so we have 4 cosine 4x minus, and the derivative here is 2x, minus 2x cosine of x squared. So what you see is this result is extremely powerful. You get plenty of output for minimal input. So again, be careful that you take the opportunity to really master this result, and also the result about even and odd functions. They will certainly pay off in your future calculations. And we are done.